Before I start talking about fundamental particles, I want to make sure everybody understands what I'm talking about. Everybody knows that atoms are made out of protons and electrons. Anybody doesn't understand that? They would admit to not understanding. Okay. The atomic nucleus is made out of neutrons and protons. And the protons and neutrons are made out of quarks. Each a proton is made out of two up quarks and one down quark. A neutron is made out of one up quark and two down quarks. An electron, I pass those out. The sheet that I passed out says fundamental particles. But everybody's known for a long time that the quarks, the higher quarks, not only you can't look at them, they break down as soon as you make them. They have a very short lifetime. So it's hard for me to think a fundamental particle can't break down into something. Yeah. To make a long story longer, I will tell you how I got started what I'm talking about. For years, everybody knew that the basic electrical charge was 1, the charge of an electron. So when I read about quarks having 2/3 of a charge and 1/3 of a charge, I thought that is ridiculous. These guys are. But then I realized that the physicists all think that's true. So if that's true, to me that means the basic charge is 1/3, not 1. If that's so, then that means the electron has three 1/3 charges on it. And so if the electron has three 1/3 charges on it, what other little things that make an electron? There are 3 of them. So that's what got me started in thinking about what is it that, what are these little things? Let's see. Okay. Yeah, my theory is that the electron is made out of what I'm calling Knucks. That's a kind of inelegant name for something. I visualize them as kind of like the little child's game, knuckle, Knucks, jacks or Knucks, and Knucks. Knuckle bones is too much a word, so that's Knucks. Anyhow, visualize them having a north and south pole axis, a gravitation axis, and an electrical axis. And so there are 2 versions. One's a positive one and one's a negative one. And also, since there are 6 different things, there are also left-hand and right-hand versions. Pass that. You all can use the dice as models for the things. 6-sided, and each side is different. So I have I started working with this theory. And I might add that I'm a chemical engineer and not a particle physicist. And the particle physicists know that. And so I've got a big NIH factor on my theory, not invented here. So, let's see what the sequence is. Okay. I looked at this fundamental particle diagram and decided that maybe the bosons are one-dimensional. The leptons are two-dimensional, and the quarks are three-dimensional. So if the bosons are, I appreciate this. My older son, he's basically a computer genius. He is. I'll tell you a side story about him. I bought an Apple computer when he was 14. Serial number 19,000 something. So he's been in it a long time. He took to it, and he wrote a program to write take one graphics program, the course into the family. Those aren't the words. Anyway, he had his own program he wrote. When TVA looked for somebody to do the programming for their barge during the World's Fair, they hired Rob, who's the best in high school, he's the best graphics programmer in Knoxville. So I appreciate it, you know. Okay, so the bosons, the photon is made of two Knucks, one positive, one negative. The gluon, which this is a speculation on my part, is 4. 2 positive, 2 negatives. The Z is 6. 3 positive, 3 negatives. The W minus, the W plus is it has a charge of 1, and so it has 5 positives and 2 negatives. The W minus is similar, just opposite, other change. And then the Higgs, I understand that's an 8. The photon is interesting. If you think about it, if I'm right, it has a positive and a negative. Okay, they're flying through space, speed of light. The two of them, as they go along, the two ducks go out away from the main direction and back. The distance that they travel is determined by how much energy they have. As they go out, they get out to a quarter of the wavelength, right? And turn around and come back. And the way they decide how to turn, they're not really people, is they count up however much energy they got in units of how much, let's say, okay, they have to count up to 1 times 10 to the 43 with each cycle, and they count in numbers of how much energy they got. So if a photon only has one, what am I thinking? one Planck of energy, it has to count up to 1 times 10 to the 43 before it turns around, which is, I think it's 1.5 miles or something like that. And it goes, okay, apparently they go back and forth all the way past the whole cycle. they don't go down and turn back around. If they did that, you'd have a negative top and a positive bottom, and you could rotate that in the electric field. You can't. So that means that, that they go all the way. They're going at the speed of light, up and down, and the speed of light, the direction they're going. And the fact that they count up and turn around is, I think that's an important part of the rest of them. What did you lose those? Okay.
Bob, does that?
You're just
What does that have to do with conservation of momentum? I mean, if they can do this at the speed of light, I mean, how do they turn around? Very quickly.
Well,
Is that future research?
that's I have a theory for that too, but I don't want to try to get into that.
Okay.
I think, I'm not gonna yeah, these things don't obey a lot of, you know, they're the basis of what, you know, the physics that we're familiar with. Okay, if the electron is, it has three things, three little knucks, then it's a triangle, and so it's flat. And I read someplace that people measuring the diameter of a proton would shoot them at each other in a atomic, one of these machines, what do you call it? Accelerator. Anyhow, and then based on how many bounces they get and how they go, they can calculate the diameter of the proton. When they tried the same thing with electrons, they get 0 diameter. Well, an electron has quite a bit less energy than a proton, and so the amount of energy that they have, less of energy they have, the bigger they are. So electrons should be bigger than a proton. It comes out at 0. To me, that says, oh, those things are flat plates, and they're passing by on their edges, so you're not going to find any thickness. It's kind of like one Planck length of thickness. They have no diameter down to 10 to the minus 18 meters. So, okay, then the electron has 3 quarks. The muon has a negative charge of 1. So I'm saying I add a pair of quarks to that. And so I get, the muon would have 4 negatives and 1 positive. And then tau would have 5 negatives and 2 positives. If you're looking at the list diagram of those things, that's the neutrinos. Okay, the electron, the muon, and tau all have a specific amount of energy, and I think that's it's kind of hard for them to hold together. One of the physicists told me that you can't have an electron with three little things with charges on them repel each other, and there's almost no way you can calculate how much force it would take. You can't. They can't be repelling each other, so they have to be emitting their electrons and their electrical charge in such a way that they don't interfere. They line up just right and don't repel. So that I think the electron, the muon, and tau have a specific amount of energy that holds them that they have to be stable. The neutrinos, on the other hand, are neutral. They have no charge. Equal number of positive and negative Knucks. The electron neutrino is 4. The muon neutrino is 6. And the tau neutrino is 8. And they can have any amount of energy. Let's see. They move in straight lines for a distance based on how much energy they have, and then turn. Obviously, the electron neutrino, they turn at 90 degrees. The muon neutrino, it's whatever, I forget what it is now. The angle for those shapes. The diagram shows them as the electron neutrino is small, the muon neutrino is larger, and tau neutrino is bigger. That's the opposite. They're actually, the more energy they have, the smaller they are. Now, the quarks, they were a different thing. I had trouble figuring out how on earth they. My first thought was maybe they're tetrahedrons. So I figured out how to make tetrahedrons in my wood shop, put them together to try to figure out. That didn't work. And so I eventually came up with the configurations that I'm showing here. The up quark is a triangle, like an electron, except it has two positives, one negative in it, and going in between that, is another one, and the up quark is a positive one. The down quark, this is the next line, has a ring of 3, and I'm calling these things, going back and forth to the middle, as an axle. I'm saying this is like a wheel with an axle in it. I think that's my best way of describing it. But the down quark has 2 of them, a positive and a negative, going back and forth in the middle. Let's see. The charm quark, if you look at the diagram there, or that chart on that I gave you on the particles, you notice that the energy for that one is really it's much higher than the up quark or the down quark. And I think what's happening there is inside the main triangle, the first outside triangle, and inside going around the axle is one more quark that's going around and it's a small orbital. It's held in place by the electrical charge rather than by gravity. And most of the energy in the charm quark is in that one in the middle. It's in a small path, and it's going fast. And I say most of the energy is there. The top quark, which has most energy of anything, uses a ring of 5 pentagon as an axle, and then it has one more inside of it. It's very small. It's very, very energetic. So that if you look at the energies between the charm quark and the top quark, you see it's a much different, very, very different. The strange quark has a ring of five, and the bottom quark has a ring of 7. And when I first started looking at this, I thought, these guys are wrong. The bottom quark should have more energy than the top quark. But the reason is that the bottom quark doesn't have the one going around inside the main ring. Let's see. Let me start. See if I ask any. If I got any questions, the puzzle looks. Okay. I have a neighbor who's a physicist, and he was kind enough to look at what I was doing. Oh, sorry. My wife takes care of me. And he said, you gotta explain, your theory has to explain how particles decay. I said, okay. I need to do that. So let me see what I'm talking about. Okay. This is the Feynman diagram for the muon decomposition to an electron. This is the Feynman diagram for it. It shows it breaks up, makes a W. Okay, and then spits out a neutrino, a muon neutrino, an electron neutrino, and an electron. So how do I explain that? Okay, here's the muon neutrino. I numbered the Knucks, 1, 2, 3, 4, 5. Okay, the thing seems to break between the 1 and the 5, and when this thing goes on, when things happen, they can add. When things are separated, they add pairs of Knucks over. They can add them as a string, positive, negative string out. Okay, so when this breaks up between the 4 and the 5, it adds a whole string. It adds the five of them here. Okay, so it adds 6, 7, 8, 9, 10, 11, 12, and 13. And other decompositions, it can make something else. It can add another pair, and apparently they can also, if things are bad enough, or conditions are such, they can switch them around. But in this case, that's what I'm showing this one. So that it adds those 6. Okay, now here's the thing fascinating me. That's the W right there. If you look back at what I've said a W is, it's got 4 negatives, plus, minus, and plus. And there was this, the decomposition there it sits, W. Like in the Feynman diagram. And then they break up into the muon neutrino, the electron, and the electron neutrino. And that's what the Feynman diagram shows. And I've done a bunch of other things like other ones, decompositions, I'm not gonna show them, but it works. I mean, I really have to admit, I didn't expect it to be that easy. I thought it wouldn't show up that way, and I had to have it come up with some kind of reason, but there it is. So, and I passed out the dice to you if you want to try to. You can put them together and make the different particles that you look at if you want to try. Well, thank you, Rob. Well, I understand this. I understand this a lot better. I had looked at my time. Okay. The proton is made of. Are there any questions at this point? Okay. The proton is made of an up quark, two up quarks, and a down quark. They're obviously they're in a triangle, except that a proton in the nucleus of an atom acts like a hard sphere. So that says that those three things, those three quarks, whatever they do, they make a hard sphere. And then we had a speaker, I guess a couple of years ago, who told us that his experiment showed that a neutron was spherical to within the thickness of a piece of paper on the Earth. I don't know if y'all remember that guy, but he spoke to us. And so the neutron is made out of three quarks. The same thing. It's now. A neutron is not stable. A neutron by itself, I think, lasts about 10 minutes. And it breaks down into a proton and an electron. And I think the reason it does is because these axles, the axle Knucks in the neutron. The proton is stable. And it's got with two up quarks and one down quark. It has 5 of the axle Knucks. I'm sorry, it's 4. Are y'all follow what I'm saying?
So these are, got 1, 2, 3, 4 of the axle.
Yeah, and the neutron has 5. I think okay. I get more and more speculation. I think the axle Knucks actually are the reason that the quarks are held together in the nucleus, in the neutron, proton, by gluons. In other words, the axle Knucks, I think, is where the gluons attach. The fact that the neutron has a couple of extrons is what makes it unstable. Now that's, as you can tell, I'm getting more and more speculative. The proton just has 1. Well, I do think. Okay. If you look at atomic nuclei, a proton by itself is stable. It'll last, essentially last forever. hydrogens have been in existence as long as things cooled off enough in the universe to have atoms. And hydrogens are stable. I mean, protons. Is that what I said? Hydrogen has one proton in it, and they stay there forever, essentially. Neutrons don't. A neutron and a proton make a deuterium. I can visualize these extra axles attaching one to the other with gluons to hold the neutron and the proton together. That makes sense. Because the axle nuts in there attached to gluons. So a neutron and a proton is stable. That's deuterium. It's been around since almost since hydrogen also. Tritium, in which you have two neutrons and one proton, is fairly stable, but it doesn't. It lasts 15 years or something like that. It's not stable. There's a very unusual nucleus, hydrogen 3, in which are two protons and one neutron, and it's stable. Okay, that one, it looks to me like that the two protons have their one extra axle, hooks up to the two on the neutron. It makes a nice stable nucleus. All the other nuclei in the atoms have to have as many neutrons as protons or more neutrons. But that one, at helium 3, has two protons and one neutron, and it's perfectly stable. So that's about okay. Now that's basically what I'm saying. How do I prove it? I have looked at the energy of the different. You can't call them bonds. They're not chemical bonds, but they're some way. I call them bonds because they're attaching one to the other. But let's see. Go back. Like in the boson, okay. The energy between the two Knux in the photon is variable. It can be a lot or a little bit. The gluon, they don't really. The physicists haven't come up with a number for a gluon. So, and then. The energy between the Knux and the Z is, I don't know if I can get into that. Let me see if any more questions. Does anybody have comments or questions?
How do we go about empirically demonstrating this, your hypothesis?
I think if you try to get a beam of electrons and see if there's try interference with, say, neutrons at different angles, you might be able to show that the electrons have some, if they're flat, might be able to show that you get interference if you're going at them from the side rather than the one in face in front of the other.
How about antimatter? Would that just reflect everything? Or
Yeah, all of these, the Knucks are their own antiparticle. But like in I saw the gluons, so these bosons are all their own antiparticles actually. I don't know how that works with well, if you're a right-handed particle and a left-handed particle, I think they still are each other's antiparticle. No, I didn't, like, I showed the electron, I didn't show the positron. It's just, it would be the little blue instead of red for the corners. And the same way the muon, just changing the colors. Yeah, each of them has a antiparticle. The neutrinos are their own antiparticle, but they still can be right-handed and left-handed. Did that answer the question?
Would the superconducting super collider have helped to determine what might be inside of these quarks?
They with the big one?
Yeah, the big one, which we didn't do, but
I don't know. I don't think so. The ones they got one where Switzerland.
yeah, the Large Hadron.
Yeah, it's pretty good.
So I've been reading that space may not be fundamental. Is that kind of connected to nukes, Knucks, and how they
Okay.
work?
Okay, I think the Knuck is a fourth dimensional particle. If you, I show it as having some size, but it's the size of the Planck length. In other words, it's the smallest thing you can get in our universe, and yet it has to be that. To have the functions that it does, it has to have substructure, and it can't have structure if it's as small as you can get. It has to be fourth dimensional. If it can count up to 1 × 10⁻43, this little thing, it's got something. It's not just some little thing. It's got to have some structure, and that structure has to be in the fourth dimension. So now what? I don't think there's any way right now that science at this point doesn't even agree on what I just said about the ducks, much less how what they're made out of, what their structure is in the fourth dimension. Yes.
Am I understanding this correctly, that these particles do combine? And if they do that, or when they do that, are charges or energy being given up? Anything you can measure?
Somehow or another, particularly like inside of the, I'm not sure I answered your question, inside the proton, if you think of the 3 particles, they're exchanging gluons. The gluons they're very ephemeral. They form. That's the force of this. That's the strong force comes from the gluons, and so they're formed. They disappear. They don't disappear. I think they collapse and form photons.
By changing state, or are they actually gone?
The energy is maintained somehow. Apparently, when they make energy, they turn into photons. Like the gluon would turn into photons. they're flying around inside the quark, the three quarks hooked together. And a photon, a proton does not radiate energy. If you have a hydrogen nucleus, it'll sit there quietly and not radiate out of its energy. So that means that all these things going on inside of there, much energy flying around, things collapsing, and they're all contained inside of the proton. So I think that what I think is that the three Knucks, the three quarks, form kind of a cage to hold the photons that are inside, and then use those photons to make new gluons, which then collapse and make photons. That energy is all retained inside the proton or the neutron. Those protons and neutrons do not radiate energy, even though all this is going on inside of there. And they do have a big part of the mass of the proton. It's not the quarks, they're little things. Is the gluons themselves inside of it that give it some mass. So it's I visualize it as a busy little place inside the proton neutron. And the other hadrons, the other particles made out of quarks and so forth, always they're unstable. They break up right away. The only ones really, the proton and neutrons are the only stable ones, and of course the neutrons are not quite stable. They last a while. I'm not sure I answered your question, but you won't ask it again.
I'm just trying to think of a way, if that would be a way to prove your theory.
Yeah.
It doesn't seem like it's possible to prove that.
How much time I got? 15 minutes. I took the energies that are listed on there for for each particle, and looking at the from both sides. I said, okay, how much energy is it the same energy between the positives and negatives in each of those bosons? So the physicists say they know exactly what that is. So I use that as a basis and then figure what the rest of them are. And so I do have, it's undecipherable really. It's on the back side of that thing I handed you out. It's almost unreadable. I do have it, yours doesn't have one. Yeah, I think the printer skipped on occasion. Each of the energy between the photons, between the positive and negative Knucks, I took the best. Okay, I figured that the positive and negative have an attraction. They're also turning. I think they're spinning on their gravity axis, so they turn so that they north or south and turn positive to negative, and then negative to negative repelling. So I looked at numbers that fit all of them, and those energies I've got them listed there. They did pretty good. I know that it's more complicated than that. Just those three repelling and attractive. But it does come out within about 1% of what the accepted values are for the energy. So I think, I didn't want to get into, it's hard to put down all those numbers. And, I mean, I did put them on the back there, but and they did the same thing for the leptons. The neutrinos you can't, because they can have any energy. But the electron, muon, and tau have a specific amount of energy between that they are all the. So I used all the triangular things, the electron and also the quarks. I assume that all of them with the triangle had the same energies, and all the ones that pentagons had the same energies, and all the ones that heptagon had the same energies, and that works pretty well too. So let's see, I had some of that. It's a hard thing. It's going to be difficult for me to prove it, but it does. It does match up. They do match up the energies and also the configurations. So I will. And I will, to answer Joe's question, I think there's something as far as the fourth dimension that's that determines what angle they turn at. There's the electron, the Knuck is going to. It turns at a 120 degree angle, and the muon, it turns at whatever, I forget that angle. And I think that all is in the fourth dimension.
Yeah. What do you think about the other theories that have come up with up to 7 additional dimensions, like 11-dimensional theory?
I think, I'm probably the wrong person to ask, but I think I keep getting accused of using the string theory. But the string theory, I think that they're little strings and loops. I don't think there are little strings and loops. I think they're tied, if you tie a string, 6 of them together, you can make a Knuck. But I think well, let me put it this way. I'm not doing this. There are 2 ways of looking at these things. One is as a particle. As a chemical engineer, I think in terms of particles. The physicists, for the most part, think in terms of waves and wave functions. And just like this. Okay, that harmonica, you can describe the reed, its math, the Young's modulus and so forth. Or you can describe it as far as the sound that it makes. So what I'm looking at is the particle part, and they're looking at trying to use. It's my opinion. They're trying to use the wrong model to use with math and try to calculate it. So they're getting into all kinds of. I mean, I think if they'll use just my quark Knuck bottle, that their calculations will work a lot better for them. And I might add that the physicists might not agree with that. Okay. All right, time to quit. Any other questions?
I
Yes.
almost hesitate to ask about photons, you know, you were just talking about,
Mm-hmm.
those little, vanes, you know, windmill-like things that, light hits and makes them spin, you know, the little toys you can buy. So obviously, photons are causing it to spin, which means they must have inertia. And to have inertia at speed and mass, but it says that photons have no mass, and so if it is zero mass, 0 times a big number is still 0.
Well,
How,
the photon is carrying energy, and I mean you can convert the energy into mass. And it
oh,
does.
okay, that answers it.
I mean, it hits, you know, if a photon here hits us, it changes one of our electrons. Moves the electron up. Our I molecule has gained energy, has gained mass.
Yeah, I forgot, yeah, energy and mass are equal, and, yeah.
Yeah, I think, I really, okay, I hesitate to say this, but I'll say it. I think the universe is two waves. And so that as you know, you may or may not know it, if you send the photons through a double slit, one at a time, they still make a pattern of, what do you call it? Interference pattern, one at a time, go through the slit. I think what that is that that's saying that there are two universes, that the photon is going through one slit in one universe, the same photon is going through the other slit, and the other universe has the same. So that's my explanation for the two slit hypothesis. What do you call it? Puzzle, anyhow. Anyhow, I will stop. Unless there are other questions.
What about, so I understand like space-time is not empty, but it also is kind of boiling with virtual particles. Is that what these Knucks come from? It just kind of appear, disappear out of a function of space-time?
You can't get a quark by itself. When they smash molecules up, it makes a bunch of quarks. It makes a string of them, gluons and stuff. They just, yeah, I think I think for a photon to count up to 1 times 10 to the 43, that means that the particles it's in the fourth dimension have to be something like 1 times 10 to the 70th meters, minus 70 meters. So yeah, I think the fourth dimension is alive and well. I guess there's all sorts of things. I think Einstein's and Planck felt like G is gravitational constant is a constant, and I think it's not. It's it has to. It's kind of like Newton flow and laminar flow. Newton flow depends on what the molecules the distance between molecules is on the same order as the container. So, and I think that's true. What happens at very low, small end of the spectrum, I think the Knucks are so small that they don't, they're no longer continuous, they're lumpy. And, so I think, yeah, space-time is probably, I think the Knucks send out particles, send out magnetic, Maxwell's virtual photons with every cycle of the universe. The gravity, and I think they send out the negative, the north and south pole. Maxwell's photon, what did I say? Virtual particles, or virtual photons, which aren't photons at all. I think they're separate little things. There are a bunch of them floating, going around in the universe. So I think they're interacting all the time. So I think the universe is full of all sorts of things, of waves anyhow. I'm just sure that's it. Yeah. Okay. Well, thank you for listening to my.